By the autumn of 1940, Britain stood completely alone against Nazi Germany, and the situation at sea had become nothing short of catastrophic. Every single day, merchant vessels carrying food, fuel, and munitions from North America were being sent to the bottom of the Atlantic by Admiral Dönitz's increasingly confident U-boat fleet. The numbers told a terrifying story. In October alone, German submarines sank 63 Allied ships, totaling over 350,000 tons of desperately needed supplies. Winston Churchill later admitted that the only thing that ever truly frightened him during the entire war was the U-boat peril. The mathematics of survival were brutally simple. Britain imported roughly 55 million tons of goods annually before the war. The nation produced less than half its own food. Without constant resupply across 3,000 miles of hostile ocean, the British population would begin starving within weeks, and the war effort would collapse entirely within months. Dönitz understood this vulnerability perfectly. His strategy, which he called tonnage warfare, focused not on defeating the Royal Navy in battle, but on sinking merchant ships faster than British and American shipyards could replace them. If he could achieve this crossover point, victory was mathematically inevitable. The wolf-pack tactics Dönitz developed made his submarines devastatingly effective. Rather than attacking alone, U-boats would shadow convoys during daylight hours whilst radioing their position to headquarters. Naval Command would then vector additional submarines into position, and when darkness fell, the entire pack would surface and attack simultaneously from multiple directions. The chaos that followed gave escort vessels almost no chance of protecting their charges. During one particularly brutal engagement in October 1940, convoy SC-7 lost 20 of its 34 merchant ships in a single night. Convoy HX-79 attacked immediately afterwards, lost another 12 vessels. The crews of the merchant marine, already the most dangerous service in which to serve, faced odds that grew worse with every passing month. The Royal Navy's traditional anti-submarine methods proved woefully inadequate against these tactics. Escort vessels relied primarily on ASDIC, known today as sonar, which could detect submerged submarines by bouncing sound waves off their hulls. However, ASDIC had crippling limitations. It could only find submarines underwater, but U-boats conducted their attacks on the surface at night, where they were faster than most escort vessels and virtually invisible. Even when ASDIC did make contact, the equipment lost track of submarines during the final moments of attack runs, creating what operators grimly called the dead zone. Depth charges dropped blind into this zone, frequently missed entirely. Coastal Command aircraft offered another potential solution, but they too faced fundamental problems. Aircraft could patrol vast areas of ocean far more efficiently than surface ships, and a submarine caught on the surface by daylight was extremely vulnerable. However, U-boats simply submerged when aircraft appeared, waiting beneath the waves until the threat passed. At night, when wolf packs did their killing, aircraft were essentially useless. Pilots could not see submarines in darkness, and submarines could hear approaching aircraft engines long before any visual contact became possible. The U-boats held every advantage. Churchill established the Battle of the Atlantic Committee in March 1941, declaring the struggle against the U-boats to be of supreme importance. However, declaring importance and achieving victory were entirely different matters. What Britain desperately needed was a method to find submarines in darkness, to detect them from beyond visual range, and to attack before they could dive to safety. Conventional technology could not provide this capability. The solution would require something altogether more revolutionary, something that German naval intelligence would not anticipate until far too late. The fundamental problem facing Coastal Command pilots was deceptively simple to describe, yet fiendishly difficult to solve. A surfaced U-boat presented a target roughly 60 meters long and perhaps 6 meters wide, painted grey against a grey ocean, often obscured by waves 3 or 4 meters high. During daylight hours, a sharp-eyed crew might spot such a vessel from several miles distant under ideal conditions, giving the aircraft time to dive and attack before the submarine could crash, dive to safety. But daylight attacks were becoming increasingly rare because U-boat commanders had learned to stay submerged during vulnerable hours, surfacing only under cover of darkness to recharge their batteries, ventilate their fetid interiors, and conduct their lethal operations against convoys. At night, visual detection became essentially impossible. A pilot flying at 1,500 feet altitude in a Sunderland flying boat could see virtually nothing of the black ocean beneath. Even with perfect moonlight, which occurred perhaps 5 nights per month, spotting a low-lying submarine remained extraordinarily difficult. The mathematics were hopeless. Coastal Command calculated that a night patrol had less than a 2% chance of visually detecting a surfaced U-boat even when flying directly overhead. The submarines were winning through concealment alone. The situation grew more desperate throughout 1941. During March of that year, U-boats sank over 500,000 tons of Allied shipping. April brought another 400,000 tons destroyed. The Admiralty's internal assessments grew increasingly alarmed. At current loss rates, Britain's merchant fleet would be reduced below the minimum required for survival by early 1942. Something had to change, and quickly, or the war would be lost not on any battlefield, but in the cold waters of the mid-Atlantic. Existing attempts at night detection proved uniformly inadequate. Some aircraft carried powerful searchlights, but these required the crew to first locate the submarine by some other means before illumination became useful. Without initial detection, searchlights merely advertised the aircraft's position whilst revealing nothing below. Flares dropped by parachute could illuminate wide areas of ocean, but they also gave submarines ample warning to dive. Infrared detection equipment was tested but found wanting. The temperature difference between a submarine's hull and the surrounding ocean was insufficient for reliable detection at operationally useful ranges. Sound detection offered no solution either. The noise of aircraft engines drowned out any possibility of hearing submarines from the air, and submarines themselves produced minimal acoustic signature when surfaced. Visual methods, acoustic methods, thermal methods, all had been attempted and all had failed. The U-boats remained invisible in darkness, surfacing with impunity to devastate convoys whilst coastal command patrols flew uselessly overhead. What made this failure so agonizing was the knowledge that submarines were definitely present. Cryptanalysts at Bletchley Park, working on captured Enigma materials, could sometimes provide approximate positions of U-boat patrol lines. Convoy routing officers knew where the wolf packs were gathering. Pilots flew patrol after patrol over waters absolutely teeming with submarines and returned having seen nothing whatsoever. The prey was plentiful, but completely undetectable. The solution that eventually emerged came not from traditional military thinking, but from an entirely unexpected quarter. Radar, still a closely guarded British secret, had already proven its worth during the Battle of Britain, allowing RAF fighters to intercept Luftwaffe bombers before they reached their targets. However, those chain-home radar stations were enormous fixed installations requiring hundreds of tons of equipment. The notion of fitting radar into an aircraft seemed almost fantastical. The equipment was too heavy, too power-hungry, and too delicate for airborne use. Almost fantastical, that is, until a group of civilian scientists began working on what initially seemed an impossible engineering challenge. The scientists who would ultimately crack the night detection problem worked not in military laboratories, but in requisitioned country houses scattered across southern England. The telecommunications research establishment, operating from Swanage in Dorset, brought together some of Britain's most brilliant physicists and engineers under conditions of absolute secrecy. These men, dubbed boffins by their military colleagues, approached warfare as an engineering problem rather than a matter of tradition and doctrine. Their methods were unconventional, their hours irregular, and their results nothing short of revolutionary. Airborne radar development had actually begun before the war, with experimental sets tested as early as 1937. These primitive systems could detect large ships from considerable distances, but they were temperamental, bulky, and required constant nursing by skilled operators. The original air-to-surface vessel radar, designated ASV Mark I, entered limited service in January 1940. It weighed over 200 kilograms, consumed enormous electrical power, and could theoretically detect a large surfaced vessel from approximately 5 miles under ideal conditions. In practice, the equipment proved maddeningly unreliable. Sea returns, the radar reflections from waves themselves, cluttered the display screens and masked genuine contacts. Operators struggled to distinguish submarines from the background noise of the ocean. ASV Mark II, introduced later in 1940, represented a significant improvement. Operating on a wavelength of 1.5 meters, this system could detect a surfaced submarine from roughly 10 miles in favorable conditions. Coastal Command began fitting the equipment to its long-range patrol aircraft, including Sunderlands, Whitleys, and the American-built Catalinas, arriving through Lend-Lease. By mid-1941, radar-equipped aircraft were flying regular patrols over the Bay of Biscay, where U-boats transiting to and from their French bases were most concentrated. The results, whilst promising, remained frustratingly incomplete. Radar could indeed detect surface submarines in darkness, solving the first half of the night attack problem. An operator watching the cathode ray display would see a distinctive blip appear at range, track its movement, and guide the pilot toward the contact. Aircraft that previously flew blindly through the night could now navigate directly toward their targets with reasonable accuracy. However, radar's usefulness ended abruptly at approximately 1 mile from the target. At this critical range, sea clutter overwhelmed the submarine's return signal, and the operator lost contact precisely when he needed it most. The aircraft would be flying toward a target known to be directly ahead, but no longer visible on the radar display. The pilot faced impossible choices. Illuminating with searchlights at 1 mile gave the submarine too much warning. Diving blind toward the estimated position resulted in attacks that missed by hundreds of meters. The final moments of the approach, when accuracy mattered most, remained shrouded in uncertainty. U-boat commanders soon grasped that British aircraft were somehow locating them in darkness but seemed incapable of pressing home attacks. Standing orders evolved accordingly. When aircraft approached at night, submarines would maintain surface status until searchlight illumination confirmed detection, then crash dive with reasonable expectation of escape. The diving procedure required approximately 25 seconds to execute safely, more than enough time given the warning that searchlights provided. Radar had transformed the situation, but had not yet delivered victory. The solution to this final mile problem emerged from the mind of a middle-aged squadron leader with no scientific training but considerable practical ingenuity. Humphrey Leigh had served in the First World War and understood operational requirements in ways that laboratory scientists sometimes missed. His proposal seemed almost ridiculously simple at first glance, but its implementation would prove devastatingly effective. Humphrey de Leigh was 53 years old and serving as a personnel officer at Coastal Command Headquarters when he conceived his solution to the final mile problem. His background was entirely unremarkable for a man about to change the course of naval warfare. A former bank clerk who had learned to fly during the Great War, Leigh spent the interwar years in civilian aviation before rejoining the RAF in 1939. He possessed no scientific qualifications whatsoever, but he understood aircraft operations intimately, and he grasped the tactical problem with crystalline clarity. The existing searchlights carried by Coastal Command aircraft were naval models adapted for airborne use. They were powerful but forward-facing, requiring pilots to aim the entire aircraft toward the suspected target position. Switching them on at range gave submarines ample warning, whilst activating them too close risked overshooting targets in the moments needed for eyes to adjust to sudden brightness. Leigh proposed something fundamentally different. His design called for a searchlight mounted in a retractable turret beneath the aircraft's fuselage, capable of being trained independently of the aircraft's heading. More importantly, his light would remain dark until the final 20 seconds of attack, illuminating only when the submarine had absolutely no time to escape. The tactical concept worked as follows. Radar would track the submarine to approximately 1 mile. The aircraft would then begin its attack descent, losing altitude whilst maintaining heading toward the estimated target position. At precisely the right moment, calculated based on airspeed, altitude, and approach angle, the Leigh Light would snap on, instantly illuminating a cone of ocean approximately half a mile wide. The submarine, caught completely by surprise, would have perhaps 15 seconds before depth charges began exploding around it. 25 seconds were required for a safe crash dive. The mathematics finally favoured the attacker. Initial reception to Leigh's proposal was lukewarm at best. Senior officers questioned whether the weight of such equipment could be accommodated, whether power requirements could be met, and whether the complexity was justified given uncertain results. Leigh spent months advocating for his invention, preparing detailed technical specifications, and lobbying anyone who would listen. His persistence eventually attracted the attention of Air Marshal Philippe Joubert de la Ferté, who became Coastal Command's chief in June 1941. Joubert recognized the tactical value immediately and authorized crash development. The engineering challenges proved substantial. The light itself required 22 million candle power to illuminate targets at useful range, demanding enormous electrical generation capacity. A dedicated generator weighing several hundred kilograms had to be fitted into aircraft already laden with radar equipment, depth charges, and fuel for patrols lasting 12 hours or more. The retractable mounting mechanism added further weight and complexity. Wellington bombers, selected as the initial platform, required extensive modification at specialized facilities. Flight testing began in early 1942, with Leigh himself participating as an observer. The results exceeded expectations. Targets were illuminated clearly at ranges up to 1 mile. The light cut through fog and light rain effectively, and the surprise effect on surface vessels was complete. Crews reported that illuminated ships appeared frozen in shock during the critical seconds before attack. Training protocols were developed, operational procedures refined, and squadron crews began converting to the new equipment. The first operational patrol using the Leigh Light occurred on the night of 4th June 1942. 5 aircraft of 172 Squadron flew sweeps over the Bay of Biscay, hunting the submarines that transited these waters nightly. Shortly after midnight, radar contact was achieved. The approach procedure executed flawlessly. The light blazed forth, and for the first time, a U-boat commander discovered that darkness no longer guaranteed safety. The first Leigh Light attack achieved damage, rather than destruction, but it demonstrated the concept's terrifying potential. Within weeks, confirmed kills began accumulating. U-502 became one of the earliest victims on 6 July 1942, caught on the surface in the Bay of Biscay with absolutely no warning. The submarine's commander had mere seconds between sudden illumination and the explosion of depth charges around his vessel. There was simply no time to react. The technological balance had shifted decisively, though the full implications would take months to become apparent. Yet even as Leigh Light operations began proving their worth, British scientists were already developing something far more devastating. The cavity magnetron, invented by John Randall and Harry Boot at Birmingham University in February 1940, represented perhaps the single most important Allied technological breakthrough of the entire war. This device, small enough to hold in one hand, could generate radar signals at wavelengths of just 10 centimeters, compared to the 1.5 meters used by existing ASV Mark II equipment. The implications for submarine detection were profound. Shorter wavelengths meant dramatically improved resolution. A 10-centimeter radar could distinguish a submarine's conning tower from surrounding wave clutter far more effectively than longer wavelength systems. Detection ranges increased substantially, whilst false contacts decreased. More importantly, the German Navy had no idea this technology existed. Their scientists believed centimetric radar was theoretically impossible with current technology. When British aircraft began carrying ASV Mark III equipment in early 1943, U-boats were being detected and attacked without any understanding of how. The technical superiority was absolute. German submarines carried METOX receivers, primitive radar warning devices tuned to detect the 1.5-meter transmissions of ASV Mark II. When METOX detected incoming radar pulses, alarm bells sounded and the submarine crash dived immediately. This countermeasure had proven reasonably effective throughout 1942, restoring some measure of safety to surfaced operations. Centimetric radar operated on frequencies completely invisible to METOX equipment. Submarines equipped with functioning radar warning receivers were being destroyed, whilst their operators heard nothing whatsoever. The combination of centimetric radar with Leigh Light illumination proved catastrophically effective. Aircraft could now track submarines from 15 miles or more, approach without triggering any warning systems, and illuminate targets with perfect accuracy in the final attack seconds. U-boat commanders reported increasingly desperate situations during debriefings. Aircraft materialized from darkness without warning, lights blazed, and explosions followed within moments. Survival became a matter of pure luck, rather than skill or preparation. Admiral Dönitz grew increasingly alarmed at the mounting losses. His submarines were dying in unprecedented numbers, particularly during Bay of Biscay transits, and nobody could explain why. German naval intelligence investigated every possibility. Had the British broken Enigma codes and learned submarine positions? Were spies reporting departure times from French bases? Had some new detection method been developed? The truth that centimetric radar had rendered existing countermeasures completely obsolete eluded German scientists for crucial months. Some submarine commanders blamed METOX itself, theorizing that the receivers were somehow radiating detectable signals that British aircraft homed upon. This belief spread through the U-boat fleet, causing crews to distrust their own equipment. Dönitz eventually ordered METOX sets switched off during transits, an instruction that actually increased vulnerability to the older ASV Mark II radars still carried by some aircraft. Confusion and fear replaced the confidence that had characterized U-boat operations during the happy times of 1940 and 41. The stage was set for catastrophe. Spring 1943 would bring the reckoning that Germany had neither anticipated nor prepared for. March 1943 brought the largest convoy battles of the entire war, and initial results suggested the U-boats might yet prevail. Convoys SC-122 and HX-229, sailing within proximity of each other, were savaged by wolf packs totaling over 40 submarines. 22 merchant ships went to the bottom in a running battle lasting several days. Dönitz was elated. His tonnage warfare strategy appeared vindicated, and projections suggested Britain's lifeline might finally be severed within months. The Admiral pressed his advantage, deploying every available submarine into the North Atlantic for what he believed would be the decisive campaign. He could not have been more catastrophically mistaken. The convoy battles had masked fundamental changes in Allied capabilities. Escort groups had grown larger and better trained. Support groups equipped with dedicated anti-submarine vessels could now reinforce threatened convoys within hours. Very long-range Liberator aircraft, fitted with centimetric radar and capable of closing the mid-Atlantic air gap, were finally arriving in sufficient numbers. Most crucially, the integration of radar, Leigh Lights, improved depth charges, and decoded intelligence had reached lethal efficiency. May 1943 began with U-boats still hunting aggressively, unaware that they had become the hunted. On the first day alone, 3 submarines were destroyed. The second day brought 2 more kills. By the 5th of May, Dönitz had lost 12 submarines without corresponding success against convoys. The pattern continued relentlessly. Aircraft appeared from nowhere, catching submarines on the surface during daylight hours when they believed themselves safe from air attack. Night provided no sanctuary either. Leigh Lights blazed forth from darkness whilst radar warning receivers remained silent. The destruction reached almost industrial proportions. Convoy ONS-5, attacked by over 40 U-boats between 4th and 6th May, lost 13 merchant ships but inflicted staggering casualties in return. 6 submarines were destroyed by escort vessels. Another 2 fell to aircraft. The exchange ratio, previously favouring the attackers, had reversed completely. U-boat commanders reported almost continuous air patrols, making surface operations suicidal during daylight and merely extremely dangerous at night. Mid-May brought no respite. Between 19th and 22nd May, 11 more submarines were destroyed during attacks on convoy SC-130. The Wolfpack withdrew in disarray, having sunk merely 2 merchantmen. Dönitz received increasingly desperate reports from surviving commanders. Morale was collapsing. Crews spoke openly of their service as a death sentence. The submarine force that had nearly strangled Britain was bleeding to death in the grey Atlantic waters. On 24th May 1943, Dönitz made the decision that acknowledged defeat. He ordered all U-boats withdrawn from the North Atlantic convoy routes, conceding the campaign that had consumed German naval strategy for nearly 4 years. His war diary entry that night was stark. The losses suffered in May had reached unbearable levels. The enemy, through new detection devices, had rendered submarine warfare temporarily impossible. The final accounting for Black May was devastating. 41 U-boats destroyed in 31 days, over 2,000 trained submariners killed, captured, or missing. Aircraft accounted for roughly half these losses, predominantly through radar-guided attacks that submarines neither anticipated nor survived. The turning point was absolute and irreversible. Although U-boat operations would continue until May 1945, never again would wolf packs threaten Allied control of the Atlantic shipping lanes. Churchill received the monthly statistics with undisguised relief. The figures told the story more eloquently than any rhetoric. Merchant shipping losses plummeted, whilst submarine casualties soared. The weapon that Germany never saw had broken the U-boat threat forever. German scientists worked frantically throughout the summer of 1943 to understand what was killing their submarines. The answer, when it finally emerged, came too late to matter. Wreckage recovered from downed British aircraft revealed centimetric radar equipment that German experts had believed impossible to construct. The cavity magnetron technology was years ahead of anything German laboratories had produced. Reverse engineering efforts began immediately, but replicating such sophisticated equipment required time that Dönitz's crews simply did not have. The Metox receiver debacle illustrated German confusion perfectly. Convinced that their own radar warning equipment was somehow betraying submarine positions, crews had been ordered to cease using the devices entirely during the very months when centimetric radar rendered Metox irrelevant anyway. When replacement receivers designated Naxos finally entered service in late 1943, they could detect 10-centimeter transmissions but offered minimal practical protection. Aircraft equipped with newer radar could detect submarines at ranges exceeding 15 miles, far beyond any reasonable warning distance. Even knowing an attack was coming provided insufficient time to escape. The snorkel offered more promise as a countermeasure. This Dutch invention, captured when Germany occupied the Netherlands, allowed submarines to run diesel engines whilst submerged at periscope depth. A breathing tube extending just above the surface provided air intake and exhaust venting. Submarines equipped with snorkels could theoretically remain submerged throughout entire patrols, never exposing their hulls to radar detection. Dönitz ordered crash installation programs beginning in late 1943. Snorkel operations proved miserable for crews and only partially effective tactically. The confined atmosphere became foul within hours. Sudden wave action closing the intake valve caused engines to draw air from within the submarine, creating agonizing pressure changes that ruptured eardrums and caused widespread physical distress. More problematically, the snorkel head itself remained detectable by centimetric radar, albeit at reduced ranges. Skilled operators could identify the characteristic return signature, and attacks on snorkeling submarines became routine by 1944. Acoustic homing torpedoes, designated FIDO by the Allies, added another dimension to submarine vulnerability. These weapons, dropped from aircraft, could detect and track the noise of submarine propellers, pursuing their targets through evasive maneuvers. A submarine that successfully evaded the initial depth charge attack might still fall victim to a circling acoustic torpedo. Combined with sonobuoys that allowed aircraft to track submerged submarines, the hunters had acquired capabilities that rendered traditional evasion tactics almost worthless. The Type 21 submarine represented Germany's most ambitious countermeasure. Designed from conception for submerged operations, these revolutionary vessels featured streamlined hulls, massive battery capacity, and performance that exceeded anything the Allies possessed. A Type 21 could travel submerged at 17 knots, faster than most escort vessels, and could remain underwater for extended periods without snorkeling. Had these submarines entered service in numbers during 1943, the Atlantic battle might have taken a different course entirely. Production delays, Allied bombing of shipyards, and manufacturing difficulties ensured that only 2 Type 21 submarines conducted operational patrols before Germany's surrender. Neither achieved any success. The revolutionary technology arrived years too late, a pattern that characterized German countermeasures throughout the final war years. Every solution reached the fleet after Allied capabilities had advanced further still. Dönitz resumed Atlantic operations in autumn 1943, with modified tactics emphasizing dispersed patrols rather than concentrated wolf packs. Losses remained appalling. Between September 1943 and May 1945, German submarine casualties averaged roughly 20 vessels monthly. Young crews departed French ports, knowing statistically that most would never return. The service that had nearly won the war had become a grim exercise in attrition with no prospect of victory. The final reckoning of the U-boat war reveals destruction on an almost incomprehensible scale. Of approximately 1,100 submarines commissioned by the German Navy between 1935 and 1945, 783 were destroyed by enemy action, accident, or scuttling to avoid capture. Over 28,000 German submariners perished, representing a casualty rate exceeding 70%. No other branch of any armed service during the Second World War suffered comparable losses. The U-boat arm that had threatened to starve Britain into submission was itself annihilated. Aircraft accounted for roughly half of all submarine losses, a proportion that would have seemed fantastical in 1940 when coastal command patrols flew uselessly through darkness whilst wolf packs slaughtered convoys below. The transformation from impotence to lethality required barely 3 years, driven almost entirely by technologies that Germany neither anticipated nor understood until far too late. Radar detection, Leigh Light illumination, centimetric wavelengths, acoustic homing torpedoes, and improved depth charges combined into a system that rendered submarine operations almost suicidal. The strategic consequences extended far beyond casualty statistics. Secure Atlantic shipping lanes allowed the massive build-up of American forces in Britain that made Operation Overlord possible. The invasion fleet that crossed the English Channel on 6 June 1944 carried equipment, ammunition, and supplies that had safely traversed 3,000 miles of ocean despite every German effort at interdiction. Without victory in the Atlantic, won primarily through technological superiority, the liberation of Western Europe would have been indefinitely postponed. Squadron leader Humphrey Leigh received the Order of the British Empire for his invention, but achieved relatively little public recognition during his lifetime. The Leigh Light remained classified throughout the war, and post-war accounts often overlooked his contribution amidst the larger narratives of code-breaking and convoy tactics. He died in 1975, largely forgotten by the public whose survival his invention had helped ensure. Recent historical reassessment has restored his reputation as one of the war's most important practical innovators. The cavity magnetron's significance transcended submarine warfare entirely. British scientists shared the technology with American counterparts during the Tizard mission of September 1940, a transfer later described as the most valuable cargo ever brought to American shores. American industrial capacity mass-produced magnetrons by the tens of thousands, equipping not only anti-submarine aircraft but also night fighters, naval vessels, and ground-based radar installations throughout every theater of operations. The technological legacy shaped military electronics for decades afterward. Admiral Dönitz survived the war and succeeded Hitler as head of state during the final chaotic week of the Reich. He was convicted at Nuremberg and served 10 years imprisonment, never fully accepting that his tonnage warfare strategy had been fundamentally defeated by technologies rather than resources or resolve. His memoirs portrayed the U-boat campaign as a near success, thwarted by overwhelming Allied material superiority, an interpretation that conveniently minimized the decisive role of British scientific innovation. The survivors of both sides carried their experiences into peacetime with varying degrees of reconciliation. Former U-boat commanders and coastal command pilots occasionally met at post-war reunions, exchanging accounts of the desperate nights over Biscay, when technology and courage determined who lived and who died. The mutual respect was genuine. Both sides understood they had fought at the cutting edge of warfare's technological transformation. Britain's secret weapon was never truly a single invention, but rather an integrated system of detection, illumination, and attack that evolved continuously throughout the war. Germany never saw this weapon because its components were invisible wavelengths, silent approaches, and sudden illumination, offering no time for escape. 783 submarines discovered this truth too late. The darkness that had protected them became their grave.